Welcome to this comprehensive exploration of basic statistical analysis. This field forms the bedrock of understanding data in virtually every domain. It equips individuals with a set of essential skills crucial for navigating our data-rich world. These fundamental skills include the ability to effectively explore information, summarize complex data sets, and accurately interpret findings. Mastering these techniques enables informed decision-making across various disciplines. Statistical analysis is indispensable for researchers, data analysts, business professionals, and students alike. Descriptive statistics represent a core concept in basic statistical analysis. They provide the fundamental tools necessary to summarize and describe the main features of a dataset. This initial step helps us understand the characteristics of our data before drawing broader conclusions. One primary aspect of descriptive statistics involves measures of central tendency. These metrics pinpoint the center or typical value within a dataset. They offer a single value that attempts to describe the entire set of data by identifying the central position within that data. The mean, often called the average, is calculated by summing all values and dividing by the count of observations. It is widely used but can be sensitive to extreme values or outliers. The median is the middle value in an ordered dataset, dividing it into two equal halves. It is less affected by outliers than the mean. The mode represents the value that appears most frequently in a dataset. A dataset can have one mode, multiple modes, or no mode at all. Each measure of central tendency offers a unique perspective on the typical value, depending on the data's distribution. Beyond central tendency, measures of dispersion quantify the spread or variability within a dataset. These measures tell us how much individual data points differ from the average. Understanding dispersion is crucial for assessing the consistency and reliability of our data. The standard deviation is a widely used measure of dispersion. It indicates the average amount of variability or spread around the mean. A low standard deviation suggests data points are close to the mean, while a high standard deviation indicates greater spread. Variance is the square of the standard deviation. It measures the average of the squared differences from the mean. While less intuitive than standard deviation, variance is a critical component in many advanced statistical calculations and models. Visualizations are also integral to descriptive statistics, aiding significantly in understanding data distribution. They transform raw numbers into easily digestible graphical representations. These visual tools help us quickly grasp complex patterns and relationships. Histograms display the distribution of a numerical variable by dividing data into bins and showing the frequency of observations in each bin. They are excellent for identifying the shape, center, and spread of data. Box plots, also known as box and whisker plots, illustrate the distribution of a dataset through its quartiles. They effectively show the median, spread, and potential outliers. Scatter plots are used to display the relationship between two numerical variables. Each point on the plot represents a pair of values, revealing patterns, trends, or correlations. These visualizations collectively serve several key purposes in data analysis. They are essential for understanding the underlying distribution of data, whether it is symmetrical, skewed, or multimodal. Visualizations also help in identifying potential patterns or trends that might not be obvious from raw numbers alone. Furthermore, they are invaluable for detecting outliers, which are data points significantly different from others. Inferential statistics builds directly upon the foundation laid by descriptive statistics. While descriptive statistics summarize observed data, inferential statistics allows us to make educated guesses or inferences about a larger population. This is achieved by analyzing a smaller, representative sample of that population. This branch of statistics heavily involves probability and various statistical tests. The primary purpose is to determine the likelihood that observed results from a sample are not due to random chance. It enables us to draw broader conclusions and generalize findings beyond the immediate data collected. One of the key concepts in inferential statistics is hypothesis testing. This systematic procedure allows us to evaluate claims or assumptions about a population parameter. It provides a framework for making decisions based on sample data. Hypothesis testing begins with formulating a null hypothesis, often denoted as H0. This hypothesis typically states that there is no effect, no difference, or no relationship between variables. It represents the status quo or the default assumption. We then test this null hypothesis against an alternative hypothesis, denoted as H1 or HA. The alternative hypothesis proposes that there is an effect, a difference, or a relationship. It is what the researcher is often trying to prove. Statistical tests are then employed to determine the significance of our findings. These tests calculate a probability value, or p-value, which helps us decide whether to reject or fail to reject the null hypothesis. A small p-value suggests that the observed data is unlikely under the null hypothesis. Among the common statistical tests are t-tests, which are used to compare the means of two groups. They help determine if the observed difference between group means is statistically significant or likely due to random variation. T-tests are particularly useful when dealing with small sample sizes. Chi-square tests are another important tool, primarily used for categorical data. They assess whether there is a significant association between two categorical variables. For example, they can determine if the distribution of one variable differs across categories of another. Analysis of variance, or ANOVA, is used to compare the means of three or more groups. It extends the concept of the t-test to multiple groups, determining if at least one group mean is significantly different from the others. ANOVA is efficient for complex experimental designs. Ultimately, inferential statistics determines if observed differences or relationships are statistically significant. This means assessing whether they are unlikely to have occurred by chance alone. A finding deemed statistically significant provides stronger evidence to support the alternative hypothesis. Correlation and regression are crucial statistical techniques for exploring and quantifying relationships between variables. They move beyond simply describing data to understanding how different factors interact. These methods are fundamental for predictive modeling and understanding causality. Correlation specifically measures the strength and direction of a linear relationship between two variables. It tells us how closely two variables move together. The correlation coefficient, typically denoted as R, ranges from -1 to +1. A positive correlation, indicated by a value closer to +1, means that as one variable increases, the other tends to increase as well. A negative correlation, closer to -1, suggests that as one variable increases, the other tends to decrease. A correlation near zero indicates a weak or no linear relationship. It is vital to remember that correlation does not imply causation. While two variables may be strongly correlated, it does not automatically mean that one causes the other. There might be a third, unobserved variable influencing both, or the relationship could be purely coincidental. Regression analysis, on the other hand, models the relationship between variables to predict the value of one variable based on another. It goes a step further than correlation by attempting to establish a mathematical equation that describes the relationship. This equation can then be used for prediction. Simple linear regression is the most basic framework, involving only two variables, one independent or predictor variable and one dependent or response variable. It seeks to fit a straight line through the data points that best represents the relationship. The equation of this line allows us to predict the dependent variable's value for a given independent variable's value. The goal of simple linear regression is to minimize the sum of the squared differences between the observed values and the values predicted by the line. This method is known as the method of least squares. The slope and intercept of the regression line provide insights into the nature of the relationship. Multiple regression extends this concept by including multiple predictor variables to explain or predict the dependent variable. Instead of a single independent variable, it considers several factors simultaneously. This allows for more complex and realistic models of real-world phenomena. For example, multiple regression could predict house prices based on factors like square footage, number of bedrooms, and location. Each predictor variable has its own coefficient, indicating its individual contribution to the prediction while holding other variables constant. This technique is powerful for understanding the combined influence of several factors. Both correlation and regression are indispensable tools in various fields, from economics to social sciences and engineering. They enable analysts to identify key drivers, forecast future outcomes, and make data-driven decisions. Understanding these relationships is a cornerstone of effective data modeling. Basic statistical analysis provides a solid and indispensable foundation for understanding and applying more advanced statistical techniques. Without a firm grasp of these fundamentals, venturing into complex modeling or machine learning can lead to misinterpretations and flawed conclusions. It is the gateway to deeper data insights. These essential skills empower individuals to critically evaluate data presented in various contexts. They enable us to question assumptions, scrutinize methodologies, and assess the validity of claims. This critical perspective is vital in an age saturated with information. Furthermore, basic statistics helps in identifying potential biases within data collection or analysis. Understanding concepts like sampling bias or measurement error allows for more robust and reliable interpretations. Recognizing these pitfalls is crucial for maintaining data integrity. Equally important is the ability to communicate findings effectively and clearly. Statistical literacy allows professionals to translate complex numerical results into understandable narratives for diverse audiences. This ensures that insights are not only discovered but also shared and acted upon. Ultimately, basic statistical analysis builds essential modeling skills. It teaches the principles of representing real-world phenomena with mathematical constructs. These foundational modeling skills are transferable across many quantitative disciplines and problem-solving scenarios. It facilitates comprehensive data analysis, moving from raw observations to informed conclusions. By systematically applying descriptive and inferential methods, analysts can uncover hidden patterns and validate hypotheses. This structured approach ensures rigor in data interpretation. The application of basic statistics contributes significantly to evidence-based decision-making. In business, healthcare, policymaking, and research, decisions supported by statistical evidence are more likely to be effective and justifiable. It replaces guesswork with data-driven insights. Engaging with statistical analysis also develops a critical mindset. It fosters logical reasoning, problem-solving abilities, and a healthy skepticism towards unsubstantiated claims. This intellectual development extends beyond mere technical proficiency. Finally, basic statistical analysis is the bridge that translates raw data into actionable insights. It transforms numbers into meaningful information that can drive strategic planning, improve processes, and solve real-world problems. Mastering these skills is an investment in future success.